Hi, welcome back to MathandBolt. In today's tutorial, we'll be working on few problems on variable separation method. So let's begin with the first one. So here we have this differential equation, and there is a initial condition provided here. So using this initial condition, we will try to figure out the value of the constant of integration after we have found out the general solution. So let's first find out the general solution. So we have the given differential equation. So 1 plus e raised to the power of 2x times dy. So what we will do, we'll take the second term to the right hand side. So that will be negative 1 plus y squared times e raised to the power of x dx. Now what we'll do, we'll make sure that the coefficient of dy comprises entirely of some function of y only, and the coefficient of dx must be something which is a function of only x. So that means we need to get rid of this term 1 plus e raised to the power of 2x from the left hand side and take it to the right hand side. And on the right hand side we have the term 1 plus y squared, so that we will need to bring it to the left hand side. So it's very simple. To do that, we're going to divide both sides by 1 plus e raised to the power of 2x times 1 plus y squared. Now we'll see that on the left hand side we have dy divided by 1 plus y squared equals to negative times, and on the right hand side we have e raised to the power of x divided by 1 plus e raised to the power of 2x times dx. Now clearly we see that the coefficient of dy is 1 over 1 plus y squared, which is entirely a function of y, and that of dx is negative e raised to the power of x divided by 1 plus e raised to the power of 2x, and this is a function of x. Now what we will do, now that the differentials are in separable form, we are going to integrate both sides. So let's integrate both sides. So we're going to use the table of integrals to perform the first integration. So looking at the table of integrals, this PDF will be provided on the description link. So we have integration dx over a squared plus x squared given by 1 over a times the arctangent of x over a plus c. So if we compare with the integral on the left hand side, the value of a is equals to 1. So that means we will get tangent inverse of x plus the constant of integration c. So let's use that. So for the integral on the left hand side, we have the tangent inverse or the arctangent of our function y. We'll reserve the constant of integration for the right hand side. That will be equals to, let's take the negative sign out, integration e raised to the power of x divided by 1 plus, we have e raised to the power of 2x, so that's simply e raised to the power of x whole squared times dx. Now this is a very simple integral. We can solve it by using the method of substitution. For this, if you consider e raised to the power of x equals to some variable t, then we get, differentiating both sides, e raised to the power of dx is equals to dt. So the integral will become negative integral of dt divided by 1 plus t squared, and this is again the same formula that we can use here. So this will be equals to negative tangent inverse of t, and our t is e raised to the power of x plus the constant of integration c. So let's write down everything nicely. So we have found out that the integral on the left hand side gives us tangent inverse of y, and the integral on the right hand side gives us negative tangent inverse of e raised to the power of x plus the constant of integration c. Now we need to determine the value of this constant of integration c. In the problem, we are provided with the initial conditions that y of 0 is equals to 1. That means when our x approaches the value 0, then y approaches the value 1. So let's substitute this value into our general solution. So we have tangent inverse. So y will be 1 equals to negative tangent inverse of e raised to the power of x. So that is e raised to the power of 0 plus the constant of integration c. So e raised to the power 0 is 1 only. Now tangent inverse of 1, that's pi over 4, which is equals to negative pi over 4 plus the constant of integration c. And solving for c, we get pi over 2. So therefore, the final solution will be tangent inverse of y plus tangent inverse of e raised to the power of x equals to, the c will be pi over 2. And this is the required solution. Let's move on to the next problem. Problem number 2. So here we have another differential equation given by 1 plus y squared times 1 plus log of x whole multiplied to dx plus x times dy equals to 0 with this initial conditions. When x equals to 1 gives the value 1. So let's begin. So we will first begin by taking this particular second term to the right hand side. So we have 1 plus y squared times 1 plus log x dx equals to negative x dy. Then we're going to divide both sides with this 1 plus y squared times x. So that should give us 1 plus log of x whole divided by x times dx equals to negative dy divided by 1 plus y squared. So you can see that the coefficient of dx is entirely a function of x. Similarly, the coefficient of dy, which is negative 1 over 1 plus y squared, is a function of y. Now they are in the separable form. So that means we can integrate both sides. So let's do that. To integrate the first function, we are going to make an assumption here. So let 1 plus log of x is equals to, let's say, some variable u. Differentiating both sides would give us 1 over x times dx is equals to du. So that means our entire integral now becomes, so 1 plus log x is u and dx over x is du. And that is equals to negative integral dy over y square. Just as the previous problem, this will be very simple. So let's not integrate it. Let's keep it as it is for now. We'll integrate it together. There's a reason why I'm doing it. So integration u du, so that will be half u squared. So half u squared, so u we have taken as 1 plus log of x, so that will be whole squared, which is equals to negative. So this is simply the arctangent of y plus the constant of integration c. The reason why I didn't integrate here in this particular step is that now when you integrate this, it will yield one constant of integration, let's say a. So again, when we integrate the integral on the left hand side, this will also integrate another constant of integration. So the c is actually a combination of the constant of integration obtained from both the two integrals. So that's why there's one reason. I mean, it's not going to affect our final answer, but this is like writing in this particular fashion makes sure that we have taken care of the constants. Now we need to determine the value of this constant of integration c. For that, we are going to use the initial conditions. So we have y of 1 is equals to 1. So that simply means that when x approaches 1, y is going to approach the value 1. Let's substitute. So we have half 1 plus log of 1 whole squared equals to negative arctangent of 1 plus the constant of integration c. So we know that log of 1, this value is 0. So we have half equals to negative. So tangent inverse of 1 will be pi over 4 plus the constant of integration. So solving for c, we have pi over 4 plus half. So that means our final answer is going to be half 1 plus log x whole squared plus tangent inverse of y equals to the constant of integration c, whose value is pi over 4 plus half when we use the condition that y of 1 is equals to 1. So this is the required solution. Let's move on to the next problem. So here, problem number 3, we have another differential equation. So let's begin. So we'll first try to separate the differentials. So that gives us x times 1 plus y squared dx equals to y times 1 plus x squared dy. We're going to divide both sides with 1 plus y squared and 1 plus x squared, the product of these two functions. So that should give us x divided by 1 plus x squared dx is equals to y divided by 1 plus y squared dy. And now this is in a variable separable form. So let's integrate both sides. Now they are fairly the same integral, so we'll only do one. Then from that one we can find out the solution of the other integral, the second integral on the right hand side. So we'll begin with the first one. So we are going to assume that 1 plus x squared is equals to, that's some variable t. Then differentiating both sides gives us 2x dx is equals to dt. So that means our integral becomes x dx. So that means that is half dt divided by 1 plus x squared is simply t. So that means we get half natural log of t. So t here is 1 plus x squared plus the constant of integration. Let's call it c1. So we have the integral on the left hand side that gives us half natural log of 1 plus x squared plus the constant of integration c1, and the integral on the right hand side gives us half natural log of 1 plus y squared plus the constant of integration c2. So that means these c1, and we have a constant of integration on the both sides. So we have half natural log of 1 plus x squared minus half natural log of 1 plus y squared equals to c2 minus c1. So if we take the half as the common factor from both the two terms, this half will go out. So we have half natural log of 1 plus x squared divided by 1 plus y squared. All I've done here is use the property that log of a minus log of b is simply log of a over b. So this is equals to c2 minus c1. So we are subtracting one constant c1 from another constant. So that should give us a constant c. So we have log of 1 plus x squared over 1 plus y squared equals to 2 times c. So let's try to figure out the value of this particular constant c. We are given the initial conditions. So let's look at the initial conditions. Y of 1 is equals to 0. So we have y of 1 equals to 0, which means that when x approaches 1, y is approaching the value 0. Let's plug this value in. So we have natural log of 1 plus 1 squared divided by 1 plus 0 squared equals to 2 times c. So that gives us natural log of 2 is equals to 2 times c. Solving for c, we have c is equals to half natural log of 2. So let's plug this back. We'll plug this into this particular form. So we have half natural log of 1 plus x squared divided by 1 plus y squared equals to c. In place of c, we have half natural log of 2. So that means we can cancel out the half from both sides. We have now only logarithm on both sides. So that can also be taken care of by taking the anti-log, which leaves us with 1 plus x squared divided by 1 plus y squared equals to 2. And this is going to be the required solution to a given differential equation. Let's move on to the next problem. Problem number 4. So we have derivative of y with respect to x is equals to 1 plus x plus y plus xy. So let's try to separate the differentials. For that we need to perform a little bit of manipulation here. So we have dy over dx is equals to 1 plus x. So from the third and the fourth term, we're going to take y as the common factor. So we have y times 1 plus x. So that means now we have two terms. The first term is 1 plus x. y times 1 plus x. So this will be the second term. From the first term and the second term, let's take 1 plus x as the common factor. So we have 1 in the first term plus y remaining in the second term. So this is dy over dx. Now it becomes easier to write in the separable form. So we have dy divided by 1 plus y equals to 1 plus x times dx. So we have in a separable form. Let's try to integrate both sides. So this is a fairly simple integral. That will be simply natural log of 1 plus y equals to integration of 1 dx. So that's simply x plus integration of x dx. That will be half x squared plus the constant of integration c. And this is our required solution. Let's move on to the next problem. Problem number 5. So we have here a differential equation. So let's try to separate the differentials. So we begin with y minus x times dy over dx equals to a times y squared plus a times dy over dx. So that's y minus a times y squared equals to x dy over dx plus a times dy over dx. Taking y as the common factor from the first two terms, we have 1 minus ay equals to, and we're going to take dy over dx as the common factor. So we have x plus a. Now we're going to separate the differentials. That should give us dx divided by x plus a equals to dy divided by y times 1 minus ay. So we have written the given differential equations in the separable form. So let's integrate both sides. Integration of the first of the integral on the left hand side will be natural log of x plus a equals to, however, to integrate this, use the method of partial fractions. Function 1 over y times 1 minus ay can be written as a over y plus b over 1 minus ay, and all you need to do is find out the values of a and b. So I'll straight away write out the results. So that would be integration 1 over y plus a divided by 1 minus ay dy. So that means we should get natural log of x plus a equals to integration of dy over y will be natural log of y. Then we have integration of a over 1 minus ay. So here we can use the method of substitution. So that should give us, we have, let's write it down, plus a. So integration of dy over 1 minus ay. So that should be natural log of 1 minus ay. But we also have to have this negative a on the denominator. So that plus the constant of integration c. And finally, we should get natural log of x plus a equals to natural log of y. The a and a gets cancelled. Negative natural log of 1 minus ay plus the constant of integration c. However, we could stop here and consider this as the final solution. But there is also another way. This could be written in more simpler form. To do that, all we have to do is, instead of c, we replace it with natural log of c, and it won't make much of a difference because c being a constant, natural log of c will also be another constant. So we have natural log of x plus a plus natural log of 1 minus ay, and that's equals to natural log of y plus natural log of c. Now we can combine the two terms on the left hand side as well as the two terms on the right hand side using the property that log of a plus log of b is equals to log of a times b. So we have log of x plus a times 1 minus ay. So that's equals to log of y times c. Taking the anti-log gets rid of the logarithmic function. So we have x plus a times 1 minus ay, and that's equals to y times c. And this is the final simplified form of the given differential equation. Let's move on to the next problem. Problem number 6. So let's solve this differential equation. We begin by rewriting the differential equation as x squared times 1 minus y dy. So we have taken x squared as the common factor, plus let's take this second term to the right hand side. We'll have a negative sign, and also we have y squared in both the two terms, so let's take it as the common factor, times 1 plus x squared dx. That means we have 1 minus y divided by y squared, so we have divided both sides by x squared y squared, times dy equals to negative 1 plus x squared divided by x squared times dx. So this is in the separable form, so we can integrate both sides. So let's rewrite this integral as, so we have dy over y squared minus, so we have y over y squared, so that will be dy over y equals to negative integration, so we have 1 over x squared, so that's simply dx over x squared minus x squared over x squared, so that's 1, so that leaves us with dx. Now let's integrate this. It's a fairly simple integral, so the first integration will be negative 1 over y minus natural log of y equals to negative of negative 1 over x minus x plus the constant of integration c. So that means we have, if we write everything in a nice fashion, we should get natural log of y plus 1 over y equals to negative 1 over x plus the constant of integration c, and this is the required solution. Let's call it c prime, and actually it's negative c prime, which is equals to positive c. So that's the end of today's tutorial. We'll be working on a few more problems in the next one. So see you in the next tutorial. Thank you.